Math 1314, Tyler Junior College, Section 4.5, Exponential Growth and Decay. Logistic growth model continued. In the previous video, we defined the form of a logistic growth model, and we used this specific one. Just a reminder, the number on the top is called the limiting population, represents the maximum population in the setting. This setting was a city of 250,000 people, and then a flu outbreak began. I don't have the flu. Pretty sure I don't have COVID-19 either. In this function, T is the weeks that have elapsed since the first flu case, and F of T is the number of people who have had the flu. I say had because some of them may have recovered since the beginning until whenever this is counting. So how long until half the population has the flu? Well, first you're going to have to know how much half the population is. Since the limiting population is 250,000, half of 250,000 is 125,000. And since we're answering the question how long, we're solving for t, which is measuring time. So we need to solve f of t is equal to 125,000. And by the way, the amount of time it takes is independent of the population size. Doesn't matter if it's 250,000 or 10 million. 10 million. As you'll see in a moment, those two numbers will get together and create either a 2 or a 1/2. All right, so let's solve this. My function looks like that: 250,000 over 1 plus 4,000 e to the negative 1.5t equals 125,000. Now this may look intimidating to solve because the variable that we're trying to solve is part of an exponential form that's inside an addition problem which is buried in a denominator. But it's actually pretty easy to get out of, and I'm going to share a trick with you. You may have seen this trick before, you may have not. It kind of involves cross-multiplying, sort of. If you're wondering, cross-multiplying, there's not two fractions here. Sure there are. Every integer can be written as a fraction by putting it over 1. So what's the trick I'm going to show you? The trick I'm going to show you is if you are solving a proportion, which by definition is two ratios equal to each other. Translation: if your equation is one fraction equals another fraction, you can move any part of either fraction diagonally across the equal sign. I know we could cross multiply, and that would work here, but I'm focusing on getting the t by itself. Normally in cross multiplying, you would multiply one denominator times one numerator, and then one denominator times the other numerator and vice versa. I know there are math professors out there that cringe at the phrase cross multiplying. If you happen to be taking one of them, your reply is, okay, what I mean is I multiply both sides of the equation by both denominators, and the result is the cross products are equal. And then watch them kind of look at you. But anyway, we could cross multiply, but here's the gimmick I wanted to show you. Cross multiplying is just a special version of a more general gimmick. The more general gimmick is when you are solving a proportion, you may move any piece along either diagonal. For example, I may move this 250,000 down here and multiply it times the 1. Or I can move this guy up here and multiply it times the 120,000, or 125,000. Or I can move the 125,000 under here and put it next to that addition problem, leaving a 1 behind. So I think more generally of let me move pieces along this cross image here. Anything can move across the diagonal. Now think about our goal. Our goal is to solve for t, which is currently down here. You never want to solve for something as long as it's in a denominator. So what I'm going to do is I'm going to move two pieces of this proportion. Number one, I'm going to take this denominator and move it over here. That's equivalent to multiplying both sides by the denominator. But at the same time, I'm going to take the 125,000 and move it under here. That's the same as dividing both sides by 125,000. Again, if you get a nitpicky math professor that says you can't do that, Your justification is, well, when I move something from one denominator to the other numerator, I'm just multiplying both sides by that denominator. Or if I move something from a numerator to the other denominator, I'm just dividing both sides by this numerator. Usually if you can justify a move, they'll be like, okay. If not, then just take a moral victory. All right, so let's move some pieces around. I'm going to switch these two pieces along this diagonal. 250,000 over 125,000. That'll give me 2, but it should because this was half of the population. Moving this guy over here, I get 1 plus 4,000 e to the negative 1.5t. And this is over 1, but I really don't need to write it over 1 anymore. That was just to point out that I'm in the middle of a proportion. That's 2. And it really wouldn't have mattered the size of the population. Anytime you take a population and divide it by half of it, you'll always get 2. Hey, look, it's a little bitty exponential equation. Let's see how quickly we can solve it. We need to isolate the exponential term. So I have to get rid of the 4,000 and the 1. The 1 is easy, subtract 1 from both sides. Now we get 1 equals 4,000 e to the negative 1.5t. And I don't know for which time it is. I think this is the 5th time we've solved an equation of this format in this series of videos. We're solving an exponential equation that's going to use the exact same moves we've been doing. Divide by the 4,000, take the natural log of both sides, and then divide by negative 1.5. I refer you back to the first video in this series, no, the second video in this series, or in the previous video series for 4.4, I believe I forget the number, but it's titled Exponential Equations Unlike Bases. We're just going to solve this verbally, and as we do the moves, we're going to write down the results. Our first move is to divide both sides by 4,000, so the 1 would get divided by 4,000. At that point, we would take the natural log of both sides, so we would take the natural log of this. That would cancel the e, and the last thing we have to do is divide by negative 1.5. I don't want to get hung up on replicating the exact same moves over and over again if we already know how the story goes. So whatever this equals is the number of weeks it would take for half the population to have been infected by the flu. Natural log of, open parentheses, 1 divided by 4,000, close parentheses, divided by negative 1.5, and we get a staggering 5.5 weeks. Kidding aside, this is why measures are taken to prevent the spreads of viruses and things. If they go unchecked, if measures are not taken, they will spread really fast. You may be wondering, where does this model come from? Answer, previous data and solving for the missing values. But you would need more data because we have 2 unknown values. But yeah, a logistic growth model is a little bit more representative of true growth than exponential growth. Exponential growth is okay in the short term, but in the long term, when there's a limit, then it's got to stop going up to infinity and slow its growth rate. All right, so logistic growth models, a little bit messier than exponential growth, but I firmly believe they are manageable.